forward. I'll talk a little bit about also some outlook into the future, some of the things we would like to do there to make this easier moving forward. So let's start off with a slight detour into history. We started off actually having Qt on embedded. That started, in the early years we actually only did Windows and X11, and Qt used native APIs to do all the drawing. So we used X11 or Windows GDI calls to get up a widget. All the drawing was done by the underlying windowing system. So QPainter was basically using GDI or X11 calls to do the drawing. And every widget actually was a native window in that model. So what you can see up there is a screenshot, from actually KDE1 times, and that was probably Qt 1 point something that was being used at that point in time. But then, around 1999, 98, we saw that embedded systems were actually becoming a bit more powerful, and they came actually into the reach of Linux and Linux running on these systems. So 240 times 320 screens, half VGA screens, were often available on some of the higher end of the system, and you did have 16 megabytes of RAM and ROM, and usually a faster processor, and some usually very limited hardware acceleration for graphics. So Linux really became an interesting option there to do embedded systems, and there were many companies looking into that instead of looking at some of the commercial real-time operating systems. But there was no UI solution available. X11 wasn't really suited for these embedded systems. I mean, the footprint of X11 just easily blew already the amount of available flash you had and RAM. But what was there was that Linux had a frame buffer, so you could draw into it, you could do things there. And we had in the early days there, that was during Trolltech times, we had a prototype which was called QImagePaint device, where we could draw into actually a memory buffer, and that fit. We got the idea that fits actually very well together. We can use that to draw 2D graphics into a raster buffer. If we put that make that raster buffer the frame buffer, we actually have something where we can draw to the screen. And that was basically the starting point, the initial idea for doing something on Qt, for Qt Embedded. And we then went to Qt Embedded and what we call the Qt windowing system. We started the development in 1999, and was trying to do a simple and lean stack. Our goal was there at that point in time to run on 8 megabytes or less of RAM and ROM. One of the things that we saw was on the frame buffer, there was no windowing system, but we wanted to have a multi-process solution available as well. So we're looking at that one and tried and build that windowing system into the Qt framework. That was the whole QWS thing in Qt, and that survived until the Qt 4 days, pretty much. Any app that you had could be the server process, could have single and multi-process modes, and it was usually done, drawing was done using software drawing onto the Linux framework. That worked out of the box. We had some abstractions in there, some screen and other classes to do limited graphics acceleration. But it was somewhat difficult to do, and it was really done for some graphics hardware at that time, end of the 90s, that could do some blit optimizations and simple things like that. Interestingly enough, we got really down to fitting a minimal stack onto a 1.4-inch floppies. Now we still remember, in these times, we went to trade shows and we handed out floppy disks containing Qt Embedded. Was interesting, seeing how that has evolved now and how much more space we have now. Soon found out that the framework alone was not enough, and we needed some demo apps. That was the Qt Palmtop environment, as it was called in that time. These days, and that was rebranded as Qtopia a little while longer. You can see some of the screenshots there of what we had, a home screen, calculator, world clock, some handwriting recognition. Actually, it didn't look all that different, from some of the things you see on smartphones nowadays. And we actually, got that released Sharp bought the Qt Palmtop environment for their Zorus PDA series in 2001. And we went from a demo to a shipping device in 6 months. I still remember the time was completely crazy. We were hacking away like nothing, trying to get this out and working, and was actually a relatively good success, especially in the Japanese market. At the same time, we also went in and started using, Qt started getting used on industrial embedded devices for all possible configurations. We had from a minimal config where we had just to, 1.5, very little RAM, 4 megs, 8 megs, to, something where people used all of this Qtopia stack on these devices. So you see, on the left-hand side, a device which used a relatively small config. The one on the right-hand side had the full Qtopia stack up and running. So that's what happened during Q2 times the early 2000s. And then there was quite a lot happening at that point in desktop land. And most of the Qt framework development was actually focused on desktop. That's where we had a lot of the revenue. We went over and shipped Qt 3 in 2002, where we had a lot of new features for existing desktop customers. Unfortunately, one thing that also happened at that point in time is that, due to that, Qt 3 became too big and too slow for many of the embedded devices. And it got mainly ignored by most of the embedded customers we had. They stayed on Qt 2 for a long time, actually all the way up until we shipped Qt 4 in 2005, where we did a pretty conscious effort to bring back most of the required speed for the embedded devices. And we had some new functionality that made it really interesting again, because many of the embedded specific features also migrated into the desktop versions and were then used throughout Qt. So for example, one of the things we did in the embedded versions, we had just one top level surface on the frame buffer that we drew into. And the child widgets were not really native widgets. I mean, it was us doing that. And that's one of the things we actually did then on the desktop ports as well. A project called Alien Widgets happened around 4.1 time frame, where we basically said, we don't need these native widgets on the windowing system. We just have one top level surface. That's a native object in the windowing system, and everything itself we manage ourselves, and we can get better performance out of that. And we actually did. So it helped us getting things resizing a lot smoother and faster, many other things, and also reduced our memory consumption, made things just a lot easier, and helped us also get things together with the embedded version. We also added a painting abstraction, Paint Engine, which was really very much tailored after or to a good degree tailored after what we had in the embedded version before. So we could draw into multiple target surfaces. There's also some stuff happening then at that time, on the segment. We had lots of demand for IP, voice over IP phones. And we actually also did our own phone at that point in time, the green phone. That was the one phone that was fully done by Trolltech. The Chinese manufacturer did the hardware, we did the software. It was a very interesting project, and it was fully functional. Actually, I still have one on my desk lying around. But what changed here was really that the UX requirements changed dramatically in this time. I mean, very demanding. People wanted to have, fluid animations. It was still pre-iPhone, but some of these things were actually showing up already in the industry. People wanted to have integrated video. They wanted to have transitions where somehow suddenly some parts of the UI just grew in size and started taking over the whole screen. Other buttons expanded, went smaller, smooth scrolling, touch-based. All of these things came at that time slowly into existence. And what we figured, it was really hard for us to do these things. At the same time, then in 2008, or one more year later, Nokia actually bought Trolltech, and where we fully shifted focus actually from the Qt development team from desktop to embedded. It was a lot of work there, get more performance out of the thing, and we did the Symbian and the Linux work for MIMO and MeeGo. There was a huge added investment then in Nokia times. Nokia basically pushed the the Qt tooling forward, the IDE Qt Creator. We did the mobility APIs, lots of the APIs that are actually interesting and now for embedded devices and mobile devices, sensor integration, accelerometer, and we went LGPL. So you know many of these things, but the one thing that also there we got into was really, damn it, how do we solve our user experience? Because the Q widgets were really not delivering what we needed them to deliver. So we did the rethinking, and we had that problem really, that we had VoIP and mobile phones showing the limits of Qt architecture. The rectangular widgets didn't work anymore. Animations were almost impossible to do, and we had no way to realize the UI design in a clean way. We tried that with Qtopia Phone Edition for the VoIP phones, or we had actually a special edition for the VoIP phones where we did this, and we did put together one user interface with many of these animations. The problem was it was not changeable. We couldn't adapt it to anything else. And any change in the UX requirements were leading to a huge rework of the whole stack on the C++ side. It was impossible to maintain. So we really had 2 research projects going on that tried to attack that. And that's a little bit, the history of how QML came up to be. We had that Kinetic project in Oslo, where people looking at QGraphics View, which is, as a scene graph, and then try to add animations, states, and transitions to it, and maybe a little bit of added sugar on top of C++, but mainly try to implement this, using C++ APIs. The QML project in Brisbane actually took a little bit more radical approach, where they introduced a new XML-based language to describe these user interfaces and the states and transitions. And they were asking the question, do we actually need a C++ API for that? Do we need a different scene graph? Should we use OpenGL directly? And, things went a little bit back and forth. We had lots of discussions internally. What came out of it in the end was the Qt Quick version 1, where we took most of the ideas from Brisbane, and we then took an idea coming from the Berlin side to change the language from XML to what you nowadays know as QML. And we used QGraphics View as the backend then still to do the drawing. You know the QML language. It's a JavaScript based. We have object trees, we have the declarative syntax, all of these things, and a small C++ API. And that was, as I said, a conscious design decision there to make sure we have a flexibility to adjust things as we go along. And then, it's easy to bind and extend that from C++. So that was one piece of the solution that we saw for, creating these kind of user interfaces. The second piece that we saw for embedded devices, that we needed to really rethink how the Windows system integration works. The Symbian port really showed that our architecture there was flawed. I mean, I see some people here in the room that actually have been working on that one, and it was extremely difficult to get that port done. It's hard to do. It took a really long time, and we saw that actually our abstractions there were not good enough to make that easy. At the same time, QWS, the Qt windowing system, and Qt Embedded was reaching its limits. It was really good in the 90s, where you had just, mostly software drawing and a limited piece of 2D acceleration. But really integrating OpenGL and, a few years ago, OpenGBG was also interesting, has pretty much disappeared again now. But that was really hard to do. And, we saw also that the porting to other operating systems was very challenging. So, I mean, people were trying to do these ports for VxWorks and QNX. It was really hard to do that. As I said, the hardware adaptation was very hard. You had basically 2 options. You write a complete port of Qt. That's 50,000 lines of code. Difficult code, hard to debug and hard to maintain code. Not very tempting. Or you hack, and that's what most people did. You'd hack Qt Embedded to suit your needs. And, it often turned out that was also tedious. And as soon as you wanted to do a little bit more hardware acceleration, little bit, had special requirements, it was really hard to do. And also they are very error prone. So, we went and we started the project Lighthouse to get a decent abstraction layer for the Windows system. a clean API to encapsulate that, and we released that one now in 4.8 for the first time. So that's now, let me see, a bit more than a year ago. And what we really saw that immediately, what proved the design there was that we got third-party Android and iOS ports done, by basically as one-man projects, giving us a lot of, validation that yes, the abstraction was right. The Windows system, we could abstract that in a good way. We also could implement an EGL full screen, backend, which used basically EGL to create a full screen surface and then OpenGL to draw into it. And the whole backend is around 2,000 lines of code. It's really small and was easy to maintain, and it provides really, really great support for hardware acceleration. What we, however, decided there was also that we do not do our own windowing system anymore inside Qt. So no, Qt frameworks by itself do not support then something where you can do multiple processes. You need to do that by creating a Windows server as a separate process and have a windowing environment there. And fortunately for us, there was a project coming from the community that really helped us there on embedded Linux. That's the Wayland project. There's a separate talk by Andy over there later on Wayland. Are you talking today or tomorrow? Yes, today. So if you have interest on all the details of how that works, go and visit his talk. But Wayland basically is a replacement now, a modern replacement for the X server, a lot leaner, smaller, targeted also for embedded devices. It has a protocol, so you can have a server which creates surfaces, manages them, composes them together, and then client applications that use that. And Wayland just got the 1.0 release out 2-3 weeks ago, something like that. We have support actually for Wayland 1.0 and in Qt built in, so getting these things up and running is not that difficult anymore and hard. So now, with Qt 5, we did, as I said, we did quite a few changes. We completely changed our architecture for all our ports to be based on QPA, on the Qt platform abstraction. In a way, as one of my developers said, this is basically that, Qt Embedded finally won the battle. Everything's based on that abstraction, and an abstraction that's suitable for the embedded side of things. We changed Qt Quick to be fully OpenGL based with a scene graph, separate rendering thread, really to try to achieve these fluid, smooth user interfaces that people are looking for. And separate then the Qt widgets and Qt Quick, so that it is possible to do a leaner stack on embedded. If you only use Qt widgets on embedded, you can also do that. Then you get a leaner stack. If you only use Qt Quick, you also get leaner stack. Because on these devices, usually you don't mix these two things. So, as I said, all the ideas we had from embedded have now entered the mainline Qt and all ports. I talked about the release timeline earlier. So let's go now back and have a look at QPA, the Qt platform abstraction, what kind of options we have there for Linux these days. We did a lot of work, and actually a lot of backends we got in there that allow us to do things on embedded Linux. We have, as a first option, DirectFB. That was actually one of the first ports that got contributed to the Qt project after we went live. I think just a few, actually the patch series came up 1 or 2 days after we went live with the Qt project, and has been maintained since. It's basically works on DirectFB, has some acceleration for blitting, has the full input handling on Linux through actually UDEV and EVDEV. So we detect the keyboards, the attached input devices, touch screens, and so on, and basically use them directly. OpenGL support is available. You can do that with some vendor integration, but you need to do a bit of work there. It doesn't really work out of the box as far as I know. And the backend is around 3,000 lines of code. So it's actually manageable size of code. It's easy to maintain, easy to modify and hack and adapt to your needs, in case you have a Linux stack with DirectFB. There's XCB, that's the full-blown option, using X11. You see also that the backend is a lot bigger. It's 18,000 lines of code. A lot of that is also because, for XCB, we need to, for example, support things like the clipboard, drag and drop. These protocols are really a lot to implement, and actually I think these two together account for a third of the size of this backend, just the clipboard and drag and drop. It's a lot of stuff. Then we have two backends, minimal and minimal EGL. They are basically designed to be as simple as possible, and it's really just there to help you get started with a custom plugin that you want to write. I mean, they don't really do anything. So minimal just basically renders into images. You can't really do anything with that, but it's a starting point if in case you need to write your own custom backend for QPA. And then we have some experimental plugins, KMS using the kernel mode setting library, OpenWF implementing the Kronos standard for which OpenWF is the Kronos standard for Windows system integration and doing a Windows server. So that one is there, and the Linux frame buffer at the backend. The two ones I wanted to spend a little bit more time talking about is actually EGLFS and Wayland. I'll steal a little bit of your things, Andy, for Wayland, but there will be a lot of things left. I think all the details will be for you to leave. So EGLFS is really EGL full screen. So it's a full screen single surface backend. If you do an application, an embedded device which runs a single UI application, single application on the UI, this is probably a good backend for you to use if you have OpenGL. So it uses OpenEGL to get the surfaces up. You can use software rasterization for drawing, OpenGL for drawing. It directly reads from the input devices, so we basically open up dev input something on Linux and detect the input devices through EVDev. As I said, it's single process only, but the good thing about it, it is very easy to integrate. It's around 2,000 lines of code, and it's really the easiest option for you to go if you have EGL available on your embedded device. Wayland is a bit more complicated. We have a QtWayland module, which actually works now with the released Wayland 1.0. It contains two things. First of all, it contains a fully functional QPA plugin for Wayland, which means, the Windows system integration to run Qt apps as Wayland clients. Supports everything, clipboard, drag and drop, touch input. It's around 7,000 lines of code, but there's no real need to do any work there on the client side. And then we have, as a second module in there, the Qt Compositor API. And that allows you with relatively little effort to build your own Wayland compositors, sort of. So if you have surfaces from different apps or several surfaces from one app, basically which one's on top, define the stacking order, define how the transitions are being done, how they're handled. And it makes it very easy to manage these surfaces and create that composition manager, basically the Wayland server. And that server is actually the one then again that opens the Linux devices and integrates with Linux EVDev. So that's there, and then we have some Qt quick integration actually. So you can, if you want to, write your compositor fully using QML. You can also write it using C++. It's around 11,000 lines of code. It's still, size-wise manageable. It's easy. It's not too hard to get into. And there's one big advantage that you also get in addition is that it's compatible with other Wayland clients and servers, the whole thing. So you could also use the Western Wayland server, run that one, and then use just Qt clients apps. They'll show up nicely on that one. You could go the other way around and create, client apps using other technologies than Qt, and run them together with the Qt apps on that server. They integrate nicely, and this is also in the long term, on the Linux side, what people hope for to replace X11 in the little bit longer term. So I think we can now try to go over and do a small demo of that. Let's see if we can get the Raspberry Pi working. It's over there. Can you switch the input, please? And then we'll try to go for 2 or 3 demos. I mean, let's see, is it coming? I think probably I need to reboot that device. I had problems with that before. Let's try. Something coming. Yay. Now the problem is I'll have to type blindly because it's a 1080p and the projector doesn't give me all that much. So I'll try if I get it all working. So log in on that Raspberry Pi. I mean, it's good to see what you can do with the Raspberry Pi nowadays. It's a really, cheap device, really $35. And so what kind of stuff do we have? Let's try the same game. So is something coming up? Yeah. So, and this time, I mean, you see it's only in the corner here. It's made for a smaller screen resolution. It's one of the QML demos we have here. Can run it. And actually works nicely with smooth animations effects. And go back to the menu and do many of these things. That's all done with a little bit of QML, and it's just running as a client application using the EGLFS backend. So, let me see now. I have to look at the names. Motion blur, yes. Can't really see that. So this is a bit larger thing that's done actually for a high resolution 1080p screen. If it comes up. Oh, I know why. I wasn't in the right working directory, and it loads external resources if I remember correctly. So it didn't find them. Yes, that looks better. So it did a little bit of calibration at the beginning, trying to figure out, what it can do. But now you see that it's actually a full screen thing. I mean, the graphics looks better on a TV screen. It's a bit dark here, but you can see it runs actually a motion blur over that earth, and it runs the whole thing nicely at 60 frames per second. And you can go in here, and I'm not sure it's going to be visible actually, but where's the thing? If you pause it, you might see that the image is slightly blurred. Here you see it, and this is done on the fly. Here you see it's less blurred because it's smaller things. And you can do some of these things just to see. Here's the code. There's an OpenGL shader running on that, which we just did define in QML. Lots of these things, and it's actually pretty simple to get that up and running. And you see what the good thing you see with this one is that you can actually get very good performance out of a hardware as cheap as the Raspberry Pi on a 1080p screen. So the output resolution 1080p, we still get 60 frames per second, smooth things that you can also use for user interfaces then. Let's have a look. Is there one other example that I can nicely show? Yeah, let's check the text editor, and then we'll actually have to switch to another device to get. So here you see a widget-based application that's also working nicely. The text editor, I can input text, I can select, copy. No, copy I can't.
Copy's Control C. So.
Copy is Control C, yeah, right. That explains it. And Control C actually exits the thing on the device because it's on the console. It also goes to the console, and that one kills the thing. So I can't really, well, maybe actually I can copy. Yeah, so now you see some of the problems with the EGL full screen because it's only one surface. It'll put that the pop-up directly on top of it. There's some work that one can do in the full screen thing to make that better. But you know, EGL full screen actually, even though it's only one surface, I mean, there's a lot of things you can do still to make it make things. I mean, you can just define inline pop-ups and stuff like that. Now, probably copied it, so let's see if pasting works. Not quite, but I mean, most of the stuff actually works here. As I said, I mean, pop-ups and stuff like that would, if you really want to make sure that we would need to make sure that they work inside that one full screen surface, and that's some work that still, one would need to do in the platform plugin. EGLFS is mainly made, for having a single surface, no pop-ups. And if you do them, in QML inside that surface, it would just work very, very nicely. For Q widgets, we would need to do a little bit of work to make sure that they render into the same surface, which is also doable. Okay, so that's the EGLFS. Let's try to see if we can get Wayland up and running here. I'll just unplug this one, and let's plug in the other one. Andy, you might need to help me get things up and running here now.
Of course.
So let's see. This one should boot now. Well, it's basically same Raspberry Pi, just a little bit of different software on it. And you know where the Wayland thing is on yours.
Hopefully. I wrote a script, so hopefully it'll work the first time.
That helps.
Say run demo.sh. Yeah, hopefully.
Yes, looks like it.
Come on!
And
I think we did not succeed.
it does something. Yes, we did.
Oh wow, it did work.
So this is basically, I think Andy, you can navigate that beast. I'll just talk a little bit. So that's actually what's called the Maze Compositor demo. It's actually, you see, it's a Doom-like landscape where you can run in around, and it's a compositor. So let's see. There was a guy running around, but now let's put some apps into that one. Here we go. I think you've seen that one before, right? And now you can focus on them, right? Yeah. And do something with them. Come on, zoom in. And here you see it expands, goes back, and you can do all sorts of, have all these applications in there. It's just a demo on how, what you can do with the Qt Compositor API to create your own, basically Windows server. And, you have actually pretty much every freedom you want in defining how it looks like. This is just fancy. But I mean, in most cases, you can just, define your own behavior between, inter-process behavior, how, processes should cooperate, work together, how surfaces should be blended together and put to the screen. Just manage the policy between the different applications if you choose so. I mean, you can also just use some default set. I mean, we have some stuff, right, Andy? Yep. Some default which just, works similar to a regular window manager. And then, if you have the Wayland backends, then in that one, also, the window handling will work nicely. So that's a little bit the demos. That's where we are and how things look right now. So I'd say thanks, Andy. Let's get back to. Can we get back to the presentation, please? So that was a little bit of the demo here. One question that also came up quite often is, what do we do if we don't have OpenGL? I mean, all of these showed a little bit also what you can do with OpenGL, the good things you can do, but there's still quite a bit of embedded hardware out there that doesn't support it. I mean, the answer is right now what does not work without OpenGL is Qt 2 on Qt 5. Requires OpenGL So if you don't have it, you will not get anything out of that. QtQuick 1 is still there and available for the moment. But there's also another alternative, and that's the one we want to promote a little bit more going forward. If you do not have OpenGL, there's still a possibility to use a software rasterizer. There's Mesa. The Mesa project has actually a pretty good software backend using the LLVM compiler available. So it basically uses the LLVM compiler suite to generate on the fly out of the GL, shaders and other things, jittered code that then runs and is distributed actually amongst all the available CPU cores that you have. So if you have multiple cores, it would be distributed. And we've seen that actually even for a single core, if you only have a single core, no GPU, it actually beats what we can do right now with the software rasterization in Qt and the QPainter API. So that allows for QtQuick. There's one drawback right now. It's pretty much untested on ARM. It works very nicely on x86. We've tested that, and it's good. It's not too hard to set up. On ARM, the latest news I have that it might work, possibly works with LLVM greater, the latest LLVM 3.1 or 3.2, but nobody has tried it yet so far. So there's some project that will do probably after Qt 5 is out, try this out, see whether we can get this to work, and figure out how to integrate that in the stack, because it actually gives you then QtQuick 2. You get everything from Qt 5, and it actually is, from all we know, faster than drawing with software, with the QPainter software implementation. So that's the thing, one thing, and then otherwise, I mean, everything else, QWidgets, everything works, and the plugins that you can then use is Wayland, which works just fine without any OpenGL. Then it would use shared memory buffers for the surfaces between the compositor and the client apps. There's a DirectFB backend that works without it, LinuxFB, and XCB if you want X11. So that's the possible options you have in this world. So let's have a little bit of a look into the future and what we want to do moving forward. As I said, we have a wide variety of QPA backends existing today, with Mac, Windows, QNX, BlackBerry. And I think it's very easy to get started on a new hardware or even a new operating system. So, as I said in the morning, cross-platform solution is, let's add Android and iOS. That's already something we're doing then. We also want to add now Qt really and do a lot of work on the quick components for touch. So we want to really make it easier to create your user interfaces using QtQuick, because I strongly believe that's the right solution for embedded devices and the embedded device space. So the touch components are right now being worked on, and we'll hopefully have something for probably for 5.1. And we want to do a strong focus there on the embedded use cases and requirements. So the other piece that really goes into this one is the tooling side of things. How cross-compiling, remote debugging, make it very easy to deploy to the device. Some stuff, how do I, basically create a flashable image for my device? How do I then modify that image? How do I basically, compile something for the device and test it very easily? For example, there's different solutions. I mean, sometimes, the really heavy one is reflash the whole device. That takes a lot of time. You probably want something faster where you basically only can copy the device, your executable over to the device, or where you basically maybe NFS mount some of your development partition and then, run things from there. So these are things we're looking into, and we want to integrate these pieces into Qt Creator as we go along. The other thing we're working on, as I said, the Android port, native run. We have the Necessitas port. We bring it to Qt 5 and fully integrate with the Android stack. That's also an option for embedded devices actually moving forward. Reason is that many of the chipset manufacturers do provide you with an Android stack for the chipset. So that would offer something where you can actually integrate with the existing Android stack on the device that you have, and we add the deployment, the solution, and you can even probably bring the apps into the Android marketplace if you so desire. But then there's a second piece that we want to look into, and that's embedded on Android. So we want to use and go back and see, can we actually do something where we only use the Android base layer? As I said, many chipset manufacturers, you ask them for a chipset, and they say, yes, we have some chipsets, and if you look at what kind of what they support on that, you usually get as an answer, we have an Android stack for that chipset. You could use that. And the problem is, I mean, for many use cases, you don't want the whole, Java, Dalvik, virtual machine, and all the other things. If you want to use Qt, we actually don't need all that much from the operating system. We need the kernel, we need the drivers, libc, OpenGL, some, OpenMax, the media frameworks, and a few other things. So our idea now is to have a look at that one and see, can we do something? Can we use that base layer only and put Qt directly on top of that base layer? So, you might have Dalvik available, but we wouldn't require it. It depends on the use case a little bit, because Dalvik does quite a few things in Android are actually implemented there. So you have, for example, audio policy management done in Java. So if you need something that automatically switches, between your Bluetooth headset, your plugged-in headset, speakers, built-in speakers, then that is there if you use it there. If you remove the Dalvik VM, you would probably need to implement that yourself again, some audio policy. But that's really up to the use case. For many embedded use cases, that's not a problem, so you can just as well remove this. We just started that work, and there's a lot of open questions there. And I mean, I would appreciate also a lot of feedback, and we would appreciate feedback on these things there, and where we should go, what people see as their needs. So if you look at, this is how the Android runtime looks. That's the Android port, basically. Standard Android picture. You might have seen that one before, the standard Android architecture picture. And for the port, we basically put the Qt frameworks there, together with the application frameworks and the apps on top, and you can basically install these apps from the marketplace if you so desire. And then we have the embedded solution, where we really want to push this a little bit lower. Make Qt use just the base libraries and the kernel, and make all the Dalvik virtual machine optional. So that's some of the stuff we're trying to do here. And let's see if I get this demo running. I'm not quite sure. So that's a Nexus, and if things go right, I can actually boot it up, and it'll boot directly into a Qt demo. It's the cinematic experience. Let's see if I can get it working. So it's booting now. I'm sorry I don't have it in bigger. I hope you can see that. Let's see if is it booting. Battery empty. It's charging. Let's see. Now, yeah, you see the Google logo. It's a Nexus. And instead of getting into the home screen, it directly boots into the... We've replaced basically the boot sequence, the surface flinger from Android, which creates the home screen with a Qt application. Here you see the Qt cinematic experience. And that uses the EGLFS backend again. And you see it running nicely and smoothly at 60 frames per second here as well. Can have something, and it's Qt quick. You have the whole thing here. For those of you who want to have a look, come here afterwards and have a look at the demo. I'll also then, we'll probably have it. I'll see if I can get it down and into our booth as well afterwards. So that's a little bit some of the things that are cooking that we're looking into, and that was the Nexus demo. And with that, I think I'd open up for questions, comments, everything you want to ask and know. And I really, as I said, I mean, this is a lot of work in progress here moving forward. And I'd really appreciate feedback on, what people would like to see in this area, so we can really look into that. Yes, Bo.
One thing that you didn't touch on here is video, both full screen and in Windows. How does the different backends cope with video. I mean, this is one thing I hear from my customers all the time. They're just asking me, what kind of hardware can I run on?
Yeah.
How can I get decent video performance?
Yes.
And I'm like, ugh, well,
it's a difficult topic. So we've been working now quite a bit and getting into the whole topic. Right now we have GStreamer as a backend supported. So if you have a okay or good GStreamer adaptation on Linux, you can do that. There's also the VA API from Intel that we're right now trying to integrate, so you get the hardware codec support integrated in that. So if you have a standard Linux stack with GStreamer and that, I mean, especially on an x86 board from with some Intel chipsets, that should work pretty well. On others, it's a bit harder. So we're right now looking into maybe hopefully being able to do some OpenMax backend for that. That's what's being used by Android, and integrate that so we can get that working. The default output for that is always into textures, and then we render these ones to the screen. There is a little bit of work that needs to be done to enable also full screen and underlay. Usually that's what you want. So if you go full screen, what you usually want is you want to render the video through hardware into an underlay, and then use a second surface as an overlay, for example, to display the video controls and stuff like that. And that requires a little bit of hardware-specific work in the multimedia backend. And we don't have a fully done solution there right now.
I have a question about the Nexus. So we have this, we experimented with this too as a Ubuntu on Android project.
Yeah.
So my question is about the Nexus, Qt Nexus. So we get this to work right away using the Ubuntu stack on Nexus. So there's a Ubuntu on Nexus, and they simply just replace the Ubuntu kernel with the Android kernel, patched back a couple of things because they're identical, and then we took that and just simply, instead of booting into X, booted into a QML demo, and so that worked right away too.
Yep.
Is that what you used for your demo?
No, what we used here is we used the stock Android, and basically this has a full Android on it, and all we did is basically when we booted, we compiled Qt for that one. It was actually done pretty much on a weekend.
So you have glibc on there, or
no, it's Bionic on there.
Okay, so you are actually be able to compile Qt on that.
Yes.
Okay, cool.
We'll need that anyway, right?
Yes.
And this is the pure Android stack. So I mean, if I in the boot script change one line, I mean, it would boot back into the regular Android stack.
That's nice.
And you have the full Android home screen. You have all of Dalvik available there, if you so want.
Mm-hmm. And just a quick question. I'm very interested in the compositor. So is that in the release, in the beta release?
It's not currently part of the beta release, but
okay.
We have it there. We're working on it. It's working with Wayland 1.0. If you have want to know more details, I'd recommend just going to Andy's talk later today.
Absolutely. Fantastic. Thank you.
More questions?
On the full Android stack approach for multiprocess, do you consider Surface Flinger or Wayland?
It's actually a good question, and we're not sure yet, honestly speaking. Both are options, and I think we need to still evaluate what makes more sense. I think it sounds right now like Wayland is just as easy as Surface Flinger, and because we have most of that available out of the box, and we on the basic Android stack we have the input devices we get that works out of the box, and we have EGL to get the surfaces up, so we have pretty much what we need, and it's just about a matter of compiling up Wayland. It's actually one thing I've also been talking about. I was at the Linux conference in Barcelona last week, and we had some talks there also with the Yocto folks in looking into that, and one of the things that what came up out of that is basically that we might be using that basically as our system to pull these whole things together, still using all the Android components, but using then Yocto to pull it together as a build system, or a system to build the stack. And that's something we'll be looking into. So we have lots of options there, and as I said, I mean, this is early research, and I really want to invite people, to give us the feedback there early on. What are their needs? What do you need? What do you want? And maybe also get involved and try to help with the whole project on Qt project. Yeah. Another one.
When we speak about embedded systems, what is the minimum requirements, hardware requirements that you see for both? If you have a graphical user interface, or even if you don't have it, just some sensors or something like that.
Okay, so if you don't have a graphical user interface, there's not a whole lot you need really. I mean, you probably, then you would be using Qt really purely for some backend things.
Yeah, especially the infrastructure you get, the networking, the signal slot mechanisms.
I mean, Qt itself, in terms of a stack, Qt core plus network, the non-graphical piece, Qt SQL, it's around 10 megabytes, I would say. So you need that somewhere on the flash. I would think, with 32 megs of RAM, you're probably good. Okay. If you have a graphical user interface, my recommendation is to have 250. And then it depends a little bit. Do you want single process, one process only, or multiple? If you have a single process, you don't need WebKit. I think you can get it into 128 megabytes. Depends a little bit also on your screen resolution, honestly saying. If you have a large screen, that takes a lot of space for the textures and everything. For small, medium-sized screen, 128 will work. Multi-process minimum is 256. That's max of RAM. And in terms of processor, any ARM CPU that you get these days will do. The question is just, I mean, the main thing, if you use Qt Quick 2 and you have OpenGL, you can get good graphics performance out of that. Pretty much all of the work is done on the GPU. The main thing then is, when you have a slower CPU, the main place where you will see it is actually on application startup times. That's where you'll really see an effect. Other things, I think you can get that working. You have to be a little bit more careful than what you do if you go down. But I mean, we had things running, let's say, 600, 700 megahertz ARM v7 plus a GPU there, and we have, things run beautifully. The Raspberry Pi here is approximately the same spec as well, and runs 1080p graphics. Good, the GPU is pretty good, but if you have a smaller screen, I mean, you can get away with a cheaper GPU as well still. So that's approximately the ballparks that I would say.
So basically this works, the QPA works with Bionic EGL. It always works? So you could basically drop it in any Android device?
That's the plan for the longer term, yes. I mean, we have just tested this on the Nexus here, but in principle, we should be able to get that working in pretty much all Android devices. That's our goal, at least.
Yeah, that's pretty impressive.
Let's see.
So, but you get the events also from the Android. You don't get it from the UDEV.
We get it from UDEV, but that's what Android uses.
Oh, that's what. Okay, I had no idea.
On the lower level, I mean, once you have Surface Flinger up and running and the Android compositor, then they come from a different place, right? Because there's only one device always that can open the input devices directly, or should open the input devices. And in that case, we just take control over that. So this one on the Nexus is a single process mode. And we have a single UI process, so we just take the input devices. If you want to have multiple processes running at the same time, then we need some sort of composition manager that manages both the input and the output surfaces. And that could be either Surface Flinger or it could be Wayland.
I'd like to follow up on the question about memory requirements. If I now have an application running with Qt 4 on an embedded device, can it depend that it will work with Qt 5 from the memory consumption and flash requirements?
On Qt 4, you're probably using QWS, right?
Yeah.
So, there's some changes there if you use QWS specific APIs that you will have to probably do some adjustments to your code base. But the reports I got so far is that actually Qt 5 on average is slightly more performant and requires slightly less memory than Qt 4.
So it means QWS is not source code compatible.
The QWS specific parts, yes. So you had some classes, QWS screen and these kind of things. If you use these classes which usually people only did if they implemented some acceleration or some backend specific implementation. That is not compatible. But on the other hand, I mean, on Qt5, creating that integration with the hardware layer through the QPA plugin architecture should be a lot easier. And you usually, what you can do is just use probably, for example, the EGLFS backend if you have a hardware that supports that, and it should pretty much work out of the box. So generating and writing that backend and writing the hardware adaptation to your specific hardware will be a lot easier in Qt5 than in Qt4.
But I can basically depend that I can use the same hardware again.
I think it should work, yes. If for the same use case, yes.
Yes, for the same use case. Okay.
Hi, you mentioned OpenVG briefly.
I mentioned what?
OpenVG?
Yes.
Is there a QPA plugin backend plan for that?
Not currently. I welcome contributions for that. We have, it's a bit difficult. OpenVG for Qt Quick, we need OpenGL, and we made that conscious choice. For software drawing, I mean, you would need a QPainter backend for that. It's possible to do, but it is some work. I mean, we have a lot of code in Qt4 around that one could probably reuse, but somebody would need to do the work. And right now I have nobody who's doing that work, or if somebody has an interest, then either do it yourself or pay somebody to do it. That's certainly possible. Yeah. But I mean, still you won't get Qt Quick 2 and the OpenGL pieces, but the rest, yeah, I think that should be doable. It's just a matter of who's willing to do the work.
ICU for Unicode is quite large package. Mm-hmm. Is it hard dependency of Qt5, or can we get a fallback from Qt4?
Currently, you can basically use Qt without ICU, and we have there's discussions whether we want to make it a hard dependency or not. The problem is some of the more advanced features that people really need, like locale dependent sorting collation, we can't really implement that ourselves. And there's two things, I mean, with ICU now. The one option is basically ICU actually allows for a lot of customization. So you can actually, there's actually an online tool even that allows you to do that and get a stripped down version of ICU. And with that, I mean, you get down from the 20 megs to a couple of megs in size. As I said, the other option would be to see whether we want to keep the current support in Qt or do something like some options. I've been thinking about some options to do that so it doesn't really take too much space. But I mean, one of the things that we currently have is in the default build, we use ICU, and then we have a lot of the built-in data still. And that is currently a waste because it's duplicated. So we should either use ICU or our built-in data depending on how you compile Qt. Having both there is certainly not what I want to have in the longer term. But let's see, I mean, no concrete solution, but with 5.0, certainly you can still, compile without ICU support or ICU enabled. Okay. If there's any more questions, just try to get hold of me afterwards. And apart from that, thank you very much.